Okay, so we're going to be doing some Henderson-Hasselbalch equations. Technically you can do them as ice problems. Henderson-Hasselbalch is just a derivation of the equilibrium problem as you would do for an acid or a base. But it's just faster and easier to think of these as Henderson-Hasselbalch problems, okay? Now, they're a little bit different than the ones we practiced in class because we don't directly have a ratio, right? So we have a ratio, but it's stated in things like molarities and volumes, right? But remember that what the ratio would normally be in is it would normally be molarity over molarity. You could also do it in moles over moles because once you join the solutions together, the volumes end up the same, right? What I would always do in any Henderson-Hasselbalch equation is if you're going to have to work to get molarities, like you would have to do dilutions and stuff, don't. Do everything in moles. Moles doesn't change, right? You have 1 mole of KOH, it's going to be 1 mole after dilution, okay? The only time it changes is when they neutralize, right? And more specifically, you can make your life really easy because most of these problems are in molarities with milliliters, right? Okay. What is molarity again? It's moles over liters, right? Okay. Well, that isn't liters, is it? It's milliliters. So what is a milliliter? Yeah, 1,000 milliliters for a liter, right? Well, let me ask you a question. What would a millimole be then? 1,000 millimoles for a mole, right? So you can actually do all these problems in millimoles. As long as you're in millimoles on both sides, doesn't matter, okay? And so if you take a molarity and multiply it by a millimole, or a milliliter, you get a millimole, okay? Does that make sense? Okay. And so I would always do all these things in millimoles and set them all up like that, okay? You don't always have to put everything in your equations too. Don't forget that. You can always do parts of it separately. So let's look at what we have, just basic problem solving, right? What do we have? What do we need? How do we get there, right? It's always the basis of all problem solving. Which somebody should really tell, like, every person on the media right now. like, somehow that's been a lost art. I don't know what's going on. There's some crazy shit going on. Okay, so you need to prepare an acetate buffer of 5.40 pH from this molarity of acetic acid and this molarity of KOH solution. So this is going to end up being your ratio, right? But you got to include volumes into it too because you're adding those two together, okay? So if you have 880 milliliters of the acetic acid, how many milliliters of KOH solution do you need to add to make a buffer of pH 5.4? The pKa of acetic acid is 4.76. By the way, this is just repeating this data, right? Be sure to use the appropriate significant figures. Okay. So the first thing we need to understand is the Henderson-Hasselbalch is pH equals pKa plus log of base over acid, right? Okay. And that ratio of base over acid, that's supposedly in molarity, okay? But it's actually a unitless once you get that ratio, right? So as long as you use something that would not change based on concentration, like moles, you can just plug those in, okay? Atoms would work, moles would work, baker's dozen, whatever, right? Don't give a shit, they cancel. Okay. So the Henderson-Hasselbalch tells us that we're going to have some sort of difference here, right? The first thing I would do is I would take the Henderson-Hasselbalch and solve for my ratio, okay? Because the ratio is going to tell us everything else we need to know. Okay, so what would my ratio be? My pH is 5.4. I'm going to subtract off from 5.4 this 4.76. By the way, in case you're curious, your problems always have slightly different numbers. It's randomly generating them for everybody. But the way you do it is the same. Okay? So what was that difference? Can anybody give that to me? Mine would be helpful, but... Okay, 0.64? Okay, thank you very much. Yeah, so that's going to be that log, that equals the log of the base over the acid, right? So how do we get rid of a log? We take 10 to the power of both sides, right? Kind of like when we did pH, H plus concentration stuff. So we're going to take 10 to the power of 0.64. And I would just leave it like that. To be honest, because you don't really need, it's not that much harder to plug into a calculator like that, right? You can solve it out. Did you guys already solve it out? What does that number end up being? 4.365? Okay. Thank you very much. And good job. You kept it in the extra sig fig that you need to make sure you don't have rounding errors. Yeah. Okay. So we got our number now of the base to acid, right? So there's 4.65 moles of base for every 1 mole of acid, right? Okay. So let's set this up. Okay, so we have millimoles. We can get millimoles of acetic acid fairly simply. We just need to take this number right here, 0.897, times 880. And that will give us millimoles of acetic acid, right? Okay. Do you guys want to do that real quick? Pull my calculator out. It was what, 4.65? That first number was 4.65. 365. 4.365. Okay. And then we take that 0.897 times 880, and that would give us 789, right? 0.36 millimoles of acetic acid. Okay, so what is that 4.365 number? Well, that was the millimoles of base divided by the millimoles of acid, right? That would be the ratio. Okay? And so if we want to get rid of the millimoles of acid on the bottom and get to millimoles of base, all we have to do is just take that 4.365 number and multiply that by our 789 number, right? And that would cancel millimoles of acid. That makes sense? That would leave us in millimoles of base. Okay? Okay. And so we take those two numbers, we multiply them by each other. So 789.36 times 4.365, and that gives us 3,445.5564, whatever, millimoles of base, right? Okay. So we're in millimoles, but what do we actually want? We want milliliters, right? So how do we go from millimoles to milliliters? Well, we're going to have to use the molarity here, right? Specifically, we're going to have to divide by, right? So we cancel out the moles. So we divide that 3,400 number by our 2.26 molarity. Oh, I'm sorry. I forgot to subtract first. I forgot a step. Okay. So we got our millimole number, right? Okay, you guys comfortable with that so far? Okay. Okay. So our base is supposed to be okay, so we have our acid remaining. Our base is supposed to be this number that we would use up of the acid. Okay? Okay. Sorry. Okay, so are we good up to the point where we have the ratio of the base to the acid? Okay. Yeah, I forgot a step. I guess I was not paying attention. I should have drank more coffee, I guess. All right. Here, let me put on the light real quick. Okay. So we're going to take that millimole number, that's of our, we have the ratio of the base to acid, right? Okay. And so we also have how much of the acid we started off with, right? And that's these two numbers multiplied by each other in millimoles. Okay? And when we multiplied those two numbers, they were the 789, right? Times 880. Yes. They were 789. So that's the number of millimoles of our acid, okay, that we started with. Okay, so how do we get our ratio at the end? Well, we should go ahead and define this in terms of acid, shouldn't we? Okay? So what we get as a ratio at the end is going to be the base, the conjugate base of acetic acid, divided by whatever remains, right? Okay. And so we have two different species that we have to put in here, don't we? We have the species where it's this number minus X, which would be the millimoles of KOH, right? And then we have the species that's the acid, that's just X, right? That's the conjugate base. That's what gets produced. Okay? In a nice problem, that would have been the ICE, initial change equilibrium, if you guys remember. But we don't have to do the ICE problem. Okay, so we're going to have our ratio is going to equal the base, so X, divided by the amount we started with, 789.36, minus X. Okay? Okay, so we multiply over first. All right? Oh, I should have brought my pen. Let's see if what they have here. If I get lucky, they'll have basically what I need. Yes, they do. Okay. So basically, they have what we've done here. There's their 4.4, right? Okay. Okay. And so we have the X minus that, the millimoles minus X, right? Okay. We multiply over the bottom. We distribute this number through. Notice they're just doing it in 2 sig figs. You would not want to actually do it in just 2 sig figs, right? Your rounding errors would be huge. Okay? Okay. So we would get the 4.4 times the 780. That would then be equal to X plus 4.4X, right? Is everybody good up to this point? Okay, did I lose anybody at all? This is our 4.36. This one's the, we got 789, but they've been rounding through this, so their rounding error is going to be large. And then it's that millimoles minus x on the bottom and x on the top. Remember I was talking about that, where it's the conjugate base we produce. So that's going to be x, whatever amount of base we added, right? And this is going to be the amount of acid that remains after we neutralize it. So minus the amount of base we add. That makes sense? Okay. Okay. So we wrap up our math. So it's 4.4 times the 780. I would do it individually, and I would use numbers that have more decimal places, so I don't have such a large rounding error. So that would be 4.365 times the 789.36 divided by 5.365 for these numbers, which is 1 plus the 4.365. And we get 642 millimoles of the acid, the conjugate base of the acid. That number is exactly equal to the amount of base you added, right? Because whatever conjugate base exists of that acid, you end up making that because you added KOH, right? Okay, so we have the 642 millimoles of KOH now. Okay, so now we need to get that into milliliters. And to get that into milliliters, we need to divide it by its molarity, right? Its concentration. So we divide by our concentration, which is 2.26. That would give us a number that's 284.2 essentially, in this case. That's the number of milliliters. I can go ahead and reduce my number of sig figs now. I have a log in here, which is what causes me to only have 2 sig figs, right? If you remember the rules for that, that's the number of decimal places, has to do with the, that you do for the 10 to the power of, has to do with the number you get out at the end. Okay? The single number, the whole number, singles place, doesn't get counted for sig figs when you go through a log. Okay? So, rounded to 2 sig figs, 280. That's not a sig fig right there. And that gives you your number of milliliters. Anybody have any questions? Okay.
You said you divided by the molarity?
Yeah. Basically, you can also remember that better by going, what is molarity? Moles over liters. And we're in moles, right? And you can do this. I don't know if you guys realized you could always do this. All the way back in Gen Chem, you could have done this. But you can take and cancel out the units independently of the prefixes. So if you have millimoles, you can cancel out the moles and leave the milli. Cool, huh? Because what those prefixes stand for is times 10 to the power of, right? And so they're their own multiplier. Hey, did you realize that all this time? No, you just full on been doing the prefixes every time you needed to, right? You do it on both sides, I bet. Ooh, good stuff. Did that make sense? Did we get to the end? Okay. You see where I forgot? I forgot to add in the x and explain that. I skipped ahead. I got ahead of myself.